In episode 1, the same power algorithm ran over integers, matrices, rotations, and shortest paths. The algorithm never changed, only the structure underneath it did. Today we change a structure too, but this time we extend the number system itself. A dual number has the form a plus b epsilon, where a and b are ordinary real numbers, and epsilon is a brand new element. It is not a real number, and it obeys a single strange rule. Epsilon squared equals 0.
Wait, epsilon is not 0, but epsilon squared is.
Exactly. Think of epsilon as infinitesimal, smaller than every positive real number, and yet not quite 0. Addition is exactly what you would guess. Add the two halves separately. Take a plus b epsilon and add it to c plus d epsilon. The real parts, a and c, add together to give a plus c. The epsilon parts, b and d, add together to give b plus d. Nothing surprising has happened yet.
So multiplication just expands the normal way.
At first, yes, but this is where the magic hides. Multiply a plus b epsilon by c plus d epsilon, and expand it the way you always have. The real parts multiply together to give a times c. Then two cross terms appear, a times d and b times c, each carrying a single epsilon, so they add together in the epsilon slot. And the last piece, b times d, carries two epsilons multiplied together, giving epsilon squared. But epsilon squared is 0. So that very last term simply vanishes. What remains is a times c in the real part, and a times d plus b times c in the epsilon part. So a dual number carries two pieces of information at once, a value in the real part and a slope in the epsilon part. And the one rule, epsilon squared equals 0, quietly throws away everything of second order and higher. Hold on to that vanishing term. It is the whole trick.
Why does this matter for derivatives?
Take any smooth function f and feed it a dual number, a plus b epsilon. Expand it as a Taylor series around the point a. The first term is simply f of a, the value at that point. The next term carries the first derivative, b times f prime of a times epsilon. After that comes the second derivative term, b squared over 2 times f double prime of a times epsilon squared. And every term beyond that carries epsilon cubed, or some higher power of epsilon still. Now apply the rule. Epsilon squared is 0, so epsilon cubed is 0, and every higher power of epsilon is 0 as well. Every term from the second derivative onward is multiplied by epsilon squared or something higher, so all of them vanish at once. Only the first two terms survive. Set b equal to 1. That choice marks this as the variable we are differentiating with respect to. What is left is beautifully simple. F of x plus epsilon equals f of x plus f prime of x times epsilon. Now look hard at the coefficient of epsilon. It is exactly f prime of x. The derivative. There is no limit being taken, no small step size h to choose, no subtraction of two nearly equal numbers. The derivative is not approximated. It falls out of the algebra, exact to the last digit. Let us compute one for real. Take f of x equals x cubed minus 3x plus 1, and find both its value and its derivative at x equals 2. We seed a single dual number, x equals 2 plus epsilon. The real part is 2, the point we care about, and the epsilon part is 1, the seed that says, differentiate with respect to this variable.
So we just run the same arithmetic the program already knows.
Exactly that. X times x multiplies 2 plus epsilon by itself, giving 4 plus 4 epsilon. Multiply once more by x to reach x cubed. 4 plus 4 epsilon times 2 plus epsilon gives 8 plus 12 epsilon. Notice that the epsilon part, 12, has been tracking the slope the whole way. Next, minus 3x is minus 3 times 2 plus epsilon, which is minus 6, minus 3 epsilon. And plus 1 is just 1, with no epsilon part at all. Add the three pieces together. The real parts give 8 minus 6 plus 1, which is 3. The epsilon parts give 12 minus 3, which is 9. The answer is 3 plus 9 epsilon. Read it straight off. F of 2 is 3, the real part, and f prime of 2 is 9, the coefficient of epsilon.
So the answer is just sitting there in the epsilon coefficient.
Exactly. Check it by hand if you like. The derivative of f is 3x squared minus 3, and at x equals 2, that is 12 minus 3, which is 9. The algebra computed the derivative for us, with no separate derivative formula written anywhere.
So where did the chain rule go?
Nowhere. It is hiding inside multiplication. When we multiplied two dual numbers, the epsilon part came out as a times d plus b times c. Read b and d as the slopes of the two factors, and that is exactly the product rule. The derivative of f times g is f prime g plus fg prime. We never coded that by hand. It is simply what dual multiplication already does. The standard functions follow the same pattern. To handle sine, we define it once. Sine of x plus epsilon equals sine of x plus cosine of x times epsilon. Each function ships with its own derivative sitting in the epsilon slot. Cosine carries minus sine. The exponential carries itself. The logarithm carries 1 over x. Define each elementary function once correctly, and you are finished.
But what happens once we chain several of those together?
Watch, consider sine of x squared plus the exponential of minus x. Feed in x plus epsilon, and each operation hands a dual number to the next. The value in the real part, the accumulated slope in the epsilon part. By the time the computation reaches the end, the epsilon part holds the derivative of the entire expression. The chain rule threads itself through the whole composition automatically. This is the quiet payoff. We never wrote a routine that knows how to differentiate. We only overloaded the arithmetic operators and the elementary functions on one new type. Any function built from those pieces is now differentiated for free, and the result is exact. Not a finite difference approximation that you have to nurse for accuracy. Here is the thread that ties this whole series together. Pin a single call, f of z, and ask only one question: what is z? Watch what happens when we hold the code completely fixed and change only the structure that z lives in. First, let z be an ordinary real number. Then f of z runs the usual way and returns a single thing, the value. This is the program you have always written. There is nothing about derivatives anywhere in sight, and nothing unusual is happening.
And if we swap z for a dual number instead?
Then watch closely. Let z be x plus epsilon. The source code of f does not change by a single character. The very same multiplications and additions execute. But now each one also carries an epsilon part, and f of z comes back holding two numbers, the value and the derivative together. Same code, swapped structure. We changed what z is, not what f does. And dual numbers are not a hack bolted onto the language. They are a concrete piece of algebra. You can even write a plus b epsilon as a 2 by 2 matrix, with on both diagonal entries and b in the top right corner. Then epsilon itself is the matrix with a single one in the top right and zeros elsewhere. Square that matrix and you get the zero matrix. Epsilon squared equals 0. Recovered exactly, sitting inside ordinary matrix multiplication.
Does the idea keep going to second derivatives and beyond?
It nests beautifully. If one dual number tracks a single derivative, then a dual number whose two parts are themselves dual numbers tracks the second derivative. Differentiate sine at 1 this way, and you recover the value, sine of 1, the first derivative, cosine of 1, and the second derivative, minus sine of 1, all in a single pass. Push the same idea further with Taylor jets, and you can read off derivatives of any order you like, from the same arithmetic. There is one honest limitation worth naming. What we built is forward mode. Its cost grows with the number of inputs, roughly one pass per input variable. For a function from many inputs to a single output, like a neural network loss, the mirror image technique, reverse mode, also known as backpropagation, is cheaper. Forward mode shines when you have few inputs and many outputs. Reverse mode shines when you have many inputs and one output. Same calculus, two complementary strategies.
So what kind of structure is this exactly?
Step back and notice the shape of what we did. Dual numbers add, subtract, and multiply with a 0 and a 1, and all the usual laws hold. That structure has a name. It is a ring. The arithmetic is correct because the ring axioms hold, and the derivative is correct because epsilon squared equals 0. The algebraic structure determines the algorithm. This is Stepanov's insight again, carried from exponentiation all the way to calculus. So we did not teach the computer calculus. We extended its number system by a single infinitesimal element, and differentiation fell out on its own. See the structure first, and the derivative is already there, waiting for you in the coefficient of epsilon.